discuss this, we need to introduce the notion of a planar graph. Now, a planar graph is simply a graph that can be drawn on a plane without its edges crossing. There's nothing more to this. This is a planar graph, what I just drew. This is also a planar graph, what I'm drawing here on the bottom. This, now notice that this guy, well, this is a planar graph. K4 turns out to be planar because although we drew it this way all the time, we can draw it differently. We can draw these edges in such a way that they don't cross one another. Okay, so reroute that edge and draw it that way. That will make this graph K4 planar because I've just managed to draw it on a plane in such a way that the edges don't cross. Now, you may say that this is like kind of a curved line and you don't like it. Well, it's certainly possible to draw it on a plane in such a way that the edges don't cross and are also straight. So for example, this is also K4. So if you go like, I don't know, A, B, C, D, and isomorphically identify this with like, say, this way, A, B, C, D. Okay, so I've just brought this one inside. So they are the same graph, right? So the fact that we draw it on a plain sheet of paper is just a crutch for us because we're visual beings. What a graph is really a collection of dots and this pair of special vertices selected, which we represent by drawing a line between those special pairs. Okay, so these are all K4. There is a theorem to the effect that if you can draw a graph on a plane with curved edges in such a way that the edges don't cross, you can also draw it with straight edges, although that's not an easy theorem to prove. Okay, now imagine one of those. Notice that there's also this notion of a region here when we draw these graphs on a plane. So for example, let's take K4, since we have it on the screen. There are a bunch of regions that this graph splits the plane into. So you have this region R1, R2, R3, and you have this infinite region here, call it R4, right? So there are 4 regions. Now, these regions correspond to the faces of these Platonic solids that we talked about. So let me tell you real quick how you could do this. So imagine, for example, a cube, right? Here's a cube. And suppose that that cube is inscribed in a sphere like that. Okay, so just as it's drawn here. And now, if this cube is just only, so you have these edges and the faces are transparent, if you take a light right in the middle of the sphere and shine it on the cube from the outside, what you get projected on the sphere is you get the edges projected on the sphere. Do you guys see this, that the edges get projected on the sphere? Now, if you take a source of light and shine it from here, so you imagine actually taking a cube and removing one of the faces and just splashing it, gluing it, just stretching the edges, removing one face, stretching the edges and gluing it on the wall. What you get is a planar graph that looks like that. So this is one side of this is another side of a cube, like another. So the cube projected on the wall will look like that. Okay, just as you see here on this wall. So here, this is a slightly different way of representing this projection. It's what's called a stereographic projection, but just by pointing a light here, and then see what happens where the edges go as you project that light. Now, can I ask you something? Do I have a different number of edges when I do a projection like that? So what you see on the screen from the cube, let me erase the other graphs here. So this is really a cube projected on the plane. Okay. Do I have a different number of edges? I have the same number of edges, right, as I had before when I projected it. Do I have the same number of vertices when I project it? Right, I don't lose any vertex, and they're all projected on the plane. Do I have the same number of regions when I project it on the plane? Okay, so you might say maybe one region is placed when you described it the way like removing a face and gluing it on the wall. What happened to this like face that you removed? Well, it's projected on this infinite region. Okay, so I have this infinite region. So I have these regions R1, R2, R3, R4, R5, and I have this sixth region, that is this outer infinite region. It corresponds to one of those faces. When I projected the cube like this, that's shown in this picture, right? This infinite region corresponds to just one of the faces. It's no different, right? So does this make sense, what I'm talking about here? So any comments about this so far? So we have some number of regions. What we're after is determining the relationship that must exist between the number of regions, the number of vertices, and the number of edges of any planar graph. So if I'm to draw a graph on the plane without its edges crossing, then there must be a special kind of relationship that must hold between its vertices, its edges, and the number of regions in which it splits, that graph splits the plane. Does that make sense? So that's what I'd like to prove here. So in particular, the relationship will be the following. The number of vertices minus the number of edges plus the number of regions is always going to be 2 for any planar graph. And I'm about to prove this right now. Right, so for example, for this graph, it holds this projection of a cube. It's a planar graph, it holds. You have 6 regions here. You have how many vertices? How many edges?
12.
12 edges. So does that work for this planar graph? So it works. It works for any planar graph. I'm about to prove this now. But before I start the proof, okay, did everybody check in this here? So everybody check
No,
in.
not yet. Not yet.
Yeah, please check in.
Right.
Meanwhile, okay, what's a tree? Remind me. So I have some graph G on V vertices and some number of edges. What is a tree?
It's a graph that has no cycles.
Okay, it's a connected graph that has no cycles, right?
Right.
Connected, no cycles. No cycles is a tree. Now I'd like to prove to you that if a connected graph has no cycles and has n vertices, it must have n minus 1 edges. Now, as an exercise, you prove this by induction. That's in one of your handouts. But I'd like to prove that a tree on n vertices has n minus 1 edges. I don't want to prove this by induction. People are tired of proofs by induction, and you will practice proving this by induction. I'd like to give a different proof. So here's your graph, and it's called a tree because it looks something like that, maybe like this. Okay, so this is a tree. Okay, maybe something like that. Okay, so this one is a connected graph that has no cycles. By the way, how many regions does it split the plane into? It has no cycles. There's no cycle to enclose any region with anything.
Is it just one region then?
Yeah, it's just one region. It's just that infinite region. Okay, let's set that aside. That's kind of not important for the proof I'm about to carry out. Here's how I want to show this. Okay. Because, okay, the definition of this, the structure that I have drawn, and I've just drawn one representation. If I'm not going to rely this representation, it's just an aid for me to think through it. But all I'm assuming about this structure is that it is connected and it has no cycles. Okay, that's the only assumption that I make. Well, if that's the case, I'm going to say the following. Pick any vertex, and start walking along edges, and start walking along edges until you can't go no more. Edges. Until you can't go anymore. But I'm going to say no more. Until you can't go no more. Okay. Okay. Now, first of all, tell me why I can do this. My claim is that I can keep doing this without passing through the same vertex again, ever seeing the same vertex. It must happen. that if I start pick any vertex like this guy and start walking in any direction, no matter where I go, I will never return to the same vertex. Why is that the case?
By definition of a tree.
Which part of the depth? Yes, which part?
Meaning no, you can't have a connected, like you can't have a cycle.
Yeah, you can't have a cycle. Exactly. Because you can't have a cycle, you will never return to the same vertex, right? That's one thing. The second thing is it clear that I will have to stop at some point. This process cannot continue indefinitely. Okay? This will stop. The claim is this will stop and will not pass through any vertex more than once. Through V again. In fact, in any vertex more than once, but through V it certainly won't pass, right? Do people agree? When I get to, so why is that the case? Again, let's just make sure we justify every step. It's intuitive, but it will stop because we have a finite number of vertices. And each time we're going to a different vertex when we go along the edge, right? We are never returning to that vertex, right? Because there are no cycles anywhere. So each time we have a new vertex, so we have a total finite number of vertices, so we'll have to stop at some point. Now, because we stop, consider the edge that we went through to get to that vertex from which we have no other way to go. So again, we're picking a new edge every time. So finally we stopped. That means we got to that vertex through some edge. So what we're doing, we're just removing the edge and the vertex. So remove that edge, and remove that vertex and the edge incident to it. All right, let me just simply write it in shorthand. Remove that edge and that vertex. Okay, so is it clear? But what do I mean by that edge and that vertex? When I stop at some vertex, there was an edge leading to it, so I remove both that edge and that vertex. Then go back to step one. Then repeat. Let's go back here and start over again. What does that mean? Pick any vertex, go along any edge until you can't anymore, and when you reach the end, remove that vertex that you hit the dead end with, and remove that vertex and that edge. So each time we are removing one vertex and one edge. When will I have to stop? When will this process, what will the tree look like when I stop? So every time I reach an end, I remove this. Next time, maybe I started here and went this way and say this way. So I removed this guy. Then next time, maybe I started here and I went this way and I went this way and I came down this way. So I removed this guy and so on. So I keep doing this until I can't do any more. When will this process stop? What will I be left with when this process
until we left one vertex?
Yeah, we're left with until we are left with, well, this goes on. This can continue. This will continue if I'm repeating this, or anytime I can continue until we have one vertex. So help me complete the proof. I'm repeating some process which allows me to eliminate one vertex, one edge. Next time, one vertex, one edge, one vertex, one edge, until I'm left with one vertex. So I'm removing the same number of vertices and edges, and I'm left with exactly one additional vertex. People agree? People agree that I have. So I must have one more vertex than the number of edges. Right? Then number of edges. People agree? That proves that a tree, all we needed to carry out this proof is to assume that we had a connected graph with no cycles. And we came to the conclusion that you must have exactly, that kind of graph must have exactly one more vertex than the number of edges. So n edges, so conclusion. So n vertices, verts, verts, n minus 1 edges. 3. Okay, so now we have a proof for this. We've claimed this several times. We needed a proof, and now we have it. So in case I need it, I'm going to copy this result. Now I'm going to prove what I set out to prove. Here's what I wanted to prove to you. That if G is planar, then the number of vertices minus the number of edges plus the number of regions is going to be 2. That's okay. So, okay, planar connected graph. So let's assume this guy is connected. Planar connected graph. I need that assumption. Connected graph. Although for other results, we'll drop that restriction. So it's not really a restriction. So let's talk. Let our domain of this course be planar connected graphs. So those graphs that can be drawn on the plane. Maybe I'm not able to see how to draw this graph immediately, but assuming that it's possible to draw such a graph on a plane without its edges crossing, and that graph is connected, then it must be the case that its edges and its vertices and the regions into which this graph splits the region must be related in this way. There's no other way. Okay, so let's see why that's the case. So I'm proving this with your help, so please help me out. So let me just, again, just as we had with the tree, just let me have some representation of a graph. Again, this will be a crutch. The argument will be general, but let's just draw something so that we have a picture. Maybe you have, this is a general graph. Okay, maybe it has, like this looks like that. Maybe this is like that. Maybe like that. Okay, so maybe like that. I don't know. Okay, so maybe another one like that. Okay, so it's some, like, I don't want to, some complicated graph. Okay, so I've drawn some graph. It's drawn on the plane. It's a planar graph. If I had no cycles, notice that so consider 2 cases. Case 1. If G is a tree, what's happening then? Is this formula true? Okay, so I have 2 cases. My claim is that there's no other cases possible. These are the cases. G is a connected graph. Because G is connected, it either has cycles or it doesn't have cycles. If it's connected and it doesn't have cycles, it's a tree. Otherwise, it's a connected graph with cycles. Are we all in the same case, so on the same page, that these are the only 2 cases that I can possibly have? Well, in the first case, if this is G is a tree, like that, is this formula true? How many regions does a tree split? You've just told me how many regions. I just proved to you that the number of edges will be 1 fewer than the number of vertices, and you agreed with me, right? Am I correct? So I have, let's say, n vertices, then I must have n minus 1 edges. It's a connected graph. It has no cycles. It has it must have n edges. And the regions, the number of regions is 1. So in this case, yes, it holds true. n minus 1 plus 1. So this n is my r. I'm sorry, this n is my v. This n is my v. This is my edges plus the number of regions. That works out to be 2. So there's no doubt when G is a tree, that works out. Just works out. Now, case 2 is the more interesting thing. More interesting case. In case 2, G has cycles. So let's do the following thing. And by the way, you have an inductive proof in, like, I don't know, when you Google people do inductive proofs, why? Because this is more elegant. There is an inductive proof in the slides if you want to do that, but this is a much better, well, you tell me which proof you like more. So you'll see an inductive proof and the argument that I'm about to give. Now, this is a connected graph that has cycles. So let's do the following. Take any edge that is on the verge of a cycle, along the boundary of some cycle, right? So this G has cycles. So pick any cycle that you find, any one, whatever, like any cycle, and pick any edge along that cycle and just remove it from the graph. Now, what I'd like to do is I'd like to see what happens to the number of vertices, to the number of edges, and to the number of regions into which this graph splits the plane. So this graph, the one that's drawn here, it splits the region into some number of regions, right? It splits the plane into some number of regions. I don't know how many. I mean, I've drawn this one and I can count the number of regions. Looks like 1, 2, 3, 4, 5 regions here. But in general, I'm trying to make my argument very, very general. So in general, I have some like gazillion regions maybe when I draw a graph like this. So I have some number of vertices, some number of edges, some number of regions. Now, what happens when I remove, okay, so what happens when I remove an edge along a cycle? Is it clear what I mean by along a cycle? Pick any cycle, just pick any edge out of it. Cycle. Let me move this down a little bit. Okay. So let's look at any cycle here. So let's look at this edge. Let's suppose I remove this edge. So you have a basin of water here. Let's say this region, pretend it's a pool, and this was like a dam there that I removed. This was another region. Those two regions will merge, like the water would merge. You remove the dam. So what happens? Okay, first of all, I'm not removing any vertices. So the number of vertices after this operation stays the same. I'm just removing an edge. So I have one fewer edge when I removed it. But what happens to the number of regions?
You have one common body of water, so number we just go down.
Yeah, did you say one go down, right? It will go
Yeah,
down.
we just go down.
Yes. So I have one fewer region, right? I've just combined two regions into a single region, right? So every time I remove an edge along a cycle, I'm combining them into a single region, right? Everybody agrees with this, with your claim? Okay, so I've done that. Now I go look at the graph again, look at any other cycle that might be in the graph, and I remove the edge along that cycle. Suppose that next time I pick this guy. So, well, I have this graph, by the way, inside the ocean. So I have this infinite body of water too, right? So when I remove this edge, this dam just broke. So this basin of water, this little pool that I had inside the cycle, just got merged with the entire ocean. So again, when I remove an edge, every time I remove an edge, I'm not changing the number of vertices. It's still the same, but I'm reducing the number of edges by 1, and I'm reducing the number of regions by 1 again. So this is the second edge. So second edge I removed, first edge I removed. Okay, I started here. Initial graph, initial G. Okay, then I remove the third edge. So suppose I remove this edge now. These guys will combine, right? So let's actually notate that. So now I'm moving this body of water is merged with the other one. Anyway, any time I do this, I'm not changing the number of vertices, but I'm reducing the number of edges and reducing the number of regions until I can't do it anymore. What happens when I can't do it anymore? My question is, how many edges have I removed? I still have the same number of vertices, but when I've removed enough edges so that I have no cycles left, so I continue this process only as long as I have the cycles left, right? So I'm only removing edges along the cycle. So I can only continue this until I have no more cycles left. So I'm still left with a connected graph with no cycles. What's that called again? Forgot. Connected graph. Yeah, so I'm left with a tree. How many regions does that tree have? How many regions does a tree split the plane into?
Just one.
Just one infinite region, right? There are no cycles for me to bound any region other than the infinite regions. Just have one infinite region. How many edges have I removed?
You've removed R minus 1.
R minus 1 edges.
Edges.
Exactly. So what we're claiming that V, okay, so what's true about a but for a tree, for any tree, but for any tree, V, we just proved it here, minus the number of edges, which is one smaller than the number of vertices, minus the number of edges, E minus R minus 1, this is the number of edges that we're left with, plus the number of regions is going to be 2, right? For any tree. People agree? Right? So we just showed it here, right? This is V minus E minus R plus minus 1 plus 1 equals 2, right? So what are we left with is my claim. Conclusion. V minus E plus R. You see the guys that I just made it is plus R equals 2. Do people see that this must hold then? Do people see this? This must hold because it holds for a tree, and we're down to a tree when you keep repeating this process. And for a tree, the number of vertices minus the number of edges that it has plus 1 must be equal to 2, right? Because of the lemma that we proved before. Does that make sense to people? Right? Okay. This proves Euler's formula. Right? Does that make sense? So what we have just proved is that if G is a connected planar graph, then the number of its number of vertices, its number of edges, and the number of regions in which the graph splits the plane are related this way. Okay, so we're done. Now let's move on. Now let's move on. Okay, these are examples of planar graphs here. Now I'd like to, okay, ultimately, I want to prove things like K33 is not planar. So for example, like in the other section, I did this in detail. I'm not going to do it here. Maybe I'll like insert a video from the other section into this section. This is, you've seen this puzzle before, right? This is, you have a bunch of houses and you have a bunch of utilities. You actually have 3 houses and 3 utilities, and each house must be supplied with with each one of those utilities. So you essentially have a K33 graph here, K33 graph, like this, K33. And the way the utility companies operate is that they want to dig those like pipes in such a way, like they want to like lay these pipes so that they don't intersect the pipes. So the idea is to lay out these connections on the plane in such a way that they don't intersect. Does that make sense? This puzzle, how many people have seen this before? Even if you haven't seen it, it's immediate what this puzzle says, right? The puzzle is connect the houses with the utilities in such a way that the pipes there, the connections don't intersect with one another. And that amounts to the following problem. Is K33 planar? If K33 is planar, then I can draw it in a plane without the edges intersecting, and therefore I can connect the utilities with those houses that way. If it's not planar, then that's impossible. So what we want to show that it's actually impossible, that K33 is not planar. Now, you can argue this logically, why K33 is not planar. And that's what I did in the other sections. I'm not going to do it in this section. What I'm going to do is I'm going to give a much nicer proof that K33 is not planar. And we're going to do this with your help. Now we have this main result already in place, that the number of regions in a graph, okay, and the number of edges and the number of vertices are related this way. So for example, here, how many vertices do I have? So help me out. Let's just verify it before we move on for this graph. It's just another planar graph to verify what we've already proved and know to be true. It better be the case. Here's a planar graph. How many vertices?
5.
5. How many edges? Well, actually, how many edges?
7.
3. So is
7
that
edges.
3? 3. How is it 7?
Oh.
3, 3, that's 6, that's 7,
Yeah,
and
it's
then
8.
2 more.
Oh, I didn't see those two
Yeah.
on the edge.
Yeah, these are the edges. These are the edges. I have 9 of them. So I have 9 edges. How many regions? Well, they're already numbered, so there's 6. So that works out to 2. If you take away 9 from 5 plus 6, and that works out as we have just proved, we just gave an argument that works out for any planar graph, including this one, of course. This is a planar graph because it's drawn on the plane without its edges crossing. Okay. So we just, okay, the next few slides give you an inductive proof of Euler's formula, right? This was my original intention to give a proof like everybody else. But I think that the proof that I just gave is much nicer than an inductive proof, although an inductive proof gives some insight, right? Also into the structure of the problem, unlike most inductive proofs, which like you just carry out an inductive proof and it gives you zero insight on why the problem should be the case. But anyway, the next few slides sketch out that proof, and there's even a pop quiz there to which I'll return later. One thing before I move on, I wanted to ask, because we have a couple of minutes, is you guys remember Venn diagrams, right? This is kind of like incidental. How many people remember Venn diagrams, right? So Venn diagrams, you normally draw like either 2 or 3 circles, the way they're shown here. And you talk about the intersection of A and B. So these are the points, for example, in the intersection that belong to both A and B. Then you have like these points that belong to A but not to B. Then you have those points that belong to B but not A. Then you have everything outside and so on and so forth, right? So those are the Venn diagrams. They are designed to show you every possibility of an element belonging to either one of those A's, B's, so you have a bunch of A's, B's, C's, and so on and so forth, right? So either to one of them, or 2 of them and not the others, or 3 of them and not the others, which 3, and to show you all the combinations. That's the point of Venn diagrams. So for example, in a 3 by 3 case, so this is intended to be all the points that are in B, but not in A and not in C. These are the points that are not in C, but both in A and B. These are the points that are in A, in B, and in C. So you have all the, how many regions do I have? So I have 3 sets, and I want to do all possible combinations of an element belonging. So I have 3 sets, A, B, C, and let's denote by 1 if an element X is present in the set and not otherwise. So this, for example, indicates that my X is here. It's not in A, it's not in A, it's not in B, it's not in C. Here's X. I'm going to mark it with a bunch of zeros. For that X here, that belongs to all of them, I'm going to mark like 1, 1, 1. And I'm going to put a 0 if an element is in the corresponding set, and it's not, and mark it as 0 if it's not there, and there's 1 otherwise. So for example, 0, 0, 1 corresponds to this situation where I have an element here. This is X is here. It corresponds to 0, 0, 1, and so on. Right? Does that make sense? So that's what you did with Venn diagrams, right? So whatever was the purpose for which you used it. But so again, I have, anyway, if you count, you have 8 regions, right? So this also can build a correspondence between these regions here and the bit strings of length 3. So you have 8 of them, 8 of them. And then you have 8 regions here, like this region, this region, this region, that's 3. Then you have this region, that's the 4th, 5, 6, 7, and 8th outside. So you have 8 regions. Anyway, that aside, have you guys seen like Venn diagrams with 4 circles? So you have seen ones with 2 circles and 3 circles, but I bet that you've never seen the one with 4 or more circles. Has anyone seen any such thing?
I've seen one, but like
Yeah.
I don't
Well,
quite get it. Like I feel like it doesn't have like all the possible like combinations of-
So then that's not a Venn diagram. So such
Yeah,
Venn
okay.
diagrams do not exist because it's impossible to draw them. And you can do it as an exercise from what already proved, or maybe we'll do it next time or today if time is left. It's impossible to draw like 4 circles on a plane in such a way that you account for all these 16 bit strings. Right? Does it make sense what I just said? Why account for 16 bit strings? Because you will have to split the region in 16 different regions split the plane in 16 different regions so that you account for every possibility of belonging an element to some combination of these 4 sets. Does that make sense? And that is impossible. No, actually, let's argue why this is impossible. Let's argue why this is impossible. Suppose it were possible. Suppose you could have 4 circles in such a way that you split the region, split the plane into 16 regions, right? Now, you can identify this, that this is an example with 3 circles, with a planar graph, right? Every time the circles intersect, I'm going to say that I have an edge. I'm going to say every time 2 circles intersect, I'm going to call the intersection point a vertex. And the piece of the circle that connects those points, I'm going to call an edge. How many vertices do I have? Well, in case of 3, how many vertices do I have? And how did I count? Well, I'll tell you that I have, how many vertices do I have? Twice 3, 6. Why do I say twice 3 and not exactly count like here? You will say you have 1, 2, 3, 4, 5, 6, 6 points. Yes, you have 6 points, 6 intersection points. How did I account for them?
Because each circle needs to intersect with each other circle twice.
Every 2 circles intersect at 2 points, right? If it's a Venn diagram, I want an intersection between every 2 circles. I want to have an intersection, non-trivial intersection. That is, every 2 circles will intersect at 2 points for me to have something in common between those 2 circles, right? So is it true that every 2 circles will intersect at 2 points? How many, then that must be true for every pair of circles. How many pairs of circles I have if I just had 3 circles? How many pairs, how many 2s can I pick out of 3? How many pairs of circles are there from a set of 3 circles? Well, it's this pair, then it's this pair, then it's this pair. It's only 3 pairs. 3 choose 2 pairs. Well, if I'm assuming that I can draw a Venn diagram with 4 circles, then I have 4 choose 2 pairs. 4 choose 2 is 6. And every pair intersects at 2 vertices. Then I will have 12 vertices total, right? Does that make sense? I would have 12 vertices total. But the number of edges, now what's the, I can count the number of edges too. How? Well, is it true that every vertex has degree 4 at the intersection? So every vertex is an intersection of 2 circles. So do I have a degree 4 for each vertex? So now let's account for what we have. We have 12 vertices, each of degree 4. So this is the total sum of degrees. This is the total sum of degrees, which must be twice the number of edges, right? By the handshake lemma. Do people remember? So 12 times 4 is twice the number of edges. Okay, therefore, the number of edges have to be the half of 48, half of 12 times 4. So the point is I have 24 edges. Okay, that's the bottom line. So now let's take stock of what we have. If I'm able to draw a Venn diagram with 4 circles, then I'm going to have 24 edges, 12 vertices, and 16 regions for a planar graph. That, however, is impossible because according to Euler's characteristic formula, that V minus E plus R is going to have to be 2 for any planar graph. But for this graph, that characteristic V minus E plus R is not 2. It's some other number. Therefore, that graph is not planar. Does that make sense, this argument? Right? Is everybody on the same page? I understand it's easy to miss some point somewhere, but if you return to the argument, do people feel like this is clear? Even if you miss something, right? Okay, so let's leave that aside for a second. Let's get to more. This is just an example. It's an application of Euler's formula. This is why you've never seen a Venn diagram with a valid Venn diagram. Okay, you may have seen somebody trying to draw something, but that's not a Venn diagram. So that does not. Okay, so that's not a Venn diagram. Here's what I'd like to prove today before we leave. That if you have G, if G is a planar graph on at least 3 vertices, then what must happen is that the number of its edges is at most 3 times the number of vertices minus 6. And you say, okay, whoa, hold on a second. 3 times number of vertices minus 6, where does that come from? There's nothing neat about that. Like, okay, why should that be the case? Okay, so let's see. Let me prove that that's the case. First, I want to show you something like this. So here, this should be, there's a typo here. This should be that way. Okay. So first, let me show you something. Let me talk about a degree of a region. Okay, this is one more notion that we need today, and that's it. There's nothing new here. When you draw a planar graph, so here's an example of this as a planar graph. It's a planar graph. Each region is enclosed by at least 3 edges. Right? Do people agree with this? So if I just have 2 edges willy-nilly, either like this or like this, they don't enclose a region. So I need at least 3 edges to enclose some region. The number of edges that I need to traverse in order to enclose a region completely is called the degree of that region. So for example, this region R2, what's the degree of it and why? The degree of this region is 3, because when I traverse these 3 edges, I have enclosed this region completely. This R2 region is completely enclosed. When I traverse those 3 edges, I close that circuit, and I enclose that region completely. How about R1? What is the degree of R1? So again, the degree is the number of edges I need to traverse in order to encircle a region. Now I'm talking about an infinite region, and you're like, what do you mean encircle an infinite region? How on earth do you do that? Well, you can encircle them if you traverse the edges like this, these edges, these 5 edges. Is that 5 edges? Yeah, these 5 edges. Then you will have encircled the infinite region, right? You've closed the loop. If the notion, if this idea that you have an infinite region bothers you, just simply think about drawing this graph on a sphere, and then no region will be infinite in that way. So you'll see every region like before your eyes if you rotate that ball. So just imagine this graph drawn on a sphere. Okay, just don't draw on a donut or something. Just draw it on a sphere. Sphere and the plane are the same except for one point, but I don't want to get into that. But the sphere is not the same as a donut in a very specific sense. These are, you cannot build a good mapping between the two, but I want to leave that issue aside. We'll cover that in a different course. Anyway, this R1, the degree of R1 is 5, because you will have to traverse 5 edges to enclose that region. What's the degree of region R3? Well, to enclose R3 completely, you will have to traverse this edge, right? Why do I have to traverse this edge? Because it's along this region. It borders the region. So I have to traverse every edge that borders that region. You can't just leave out the edges. So when you traverse this edge, you will have to traverse it twice in order to completely enclose region R3. And when you do this, what's the number of edges that you've traversed? Well, you have 1, 2, 3, 4. This edge is traversed. Well, contributes 2 to the degree of region R3. And then here, and then that way. And you've enclosed this region R3 completely. The degree of R3 turns out to be 5. So is it clear what a degree of a region is? So for example, let's take another graph, a simpler one. So let's take K3. This is K3. How many regions? How many regions does it split the plane?
2.
2 regions, R1 and R2, right? 2 regions. And what's the degree of this region, each one?
3.
3. 3, each one has degree 3. Okay, so I don't know. How many regions does this guy split? This is similar to the first one, but
3.
Like 3. R1, R2, and R3. R3. What's the degree of R1?
4.
What's the degree of R2?
3.
And what's the degree of R3?
5.
5, exactly. All right, so it's clear what the degree of a region means, right? Now, I'd like to claim something quite interesting. I want to claim that if you have a planar graph, then twice the number of edges is at least as big as 3 times the number of regions. That's what I want to claim. Okay, so for example, for this graph, let's take this graph. Does it work out for this graph? Twice the number. How many edges? How many edges do I have here? How many edges? I'm sorry, is there anyone there?
Yeah, the six edges.
6 edges, right? Okay, let's turn the webcams on, please. So sometimes it's like, it's not a trick question. I mean, this immediate question, you see the number of edges. So I'd like people to, so make sure that someone is there, right? Hopefully that someone is all of you. How many regions?
3.
3 regions. So does that work? Does that work? Twice number of 6, twice 6 is greater than 3 times 3. So it works. And it works for any planar graph. Now I want to argue why that's the case. And if you read this stuff like in some textbooks, there you'll get some kind of wimpy arguments why that should be the case. You will get something along the following lines. So here's an explanation. You tell me if you understand this. When you are enclosing a region by traversing the edges, each edge, what I'm about to say is true, but maybe it leaves like you're wanting for a better explanation. So every time you traverse the edges to enclose a region, you will, any of those edges that are along the border of a circuit that encloses the region, that each of those edges is on either side of it, it has 2 regions, right? So when you're going through an edge, it really, you're traversing, you have one region on one side and another region on the other side, right? So you always have like 2 regions on the side of each edge. Does that make sense? In fact, that's not quite true, but it's almost true. It's at most 2 regions. You cannot have 3 regions or more on either side of any given edge. You can't have one region. For example, this edge here is on the border of just one region, this R3. This E7 edge here borders no other region than that. But every other edge borders 2 regions. So take any other edge on this graph, in this graph, so E4 borders this region and that region. E2 borders R2 and R1, and so on. So every edge borders 2 regions or just 1 region. It cannot border like 3 regions, no matter what's happening for any planar graph. So that's one fact. Another fact is that any region being enclosed by the edges has at least 3 edges surrounding it, which is also true, right? Does every region have at least 3 edges surrounding it? You can have a region that has 4 edges surrounding it, like this one. Okay, this one splits the plane into 2 regions, R1 and R2, right? The degrees of 4, both of these regions. Okay, but you need at least 3 edges. You can't get away with just 2 edges to surround the region. And then they claim that because of those 2 facts, somehow it follows, and it does follow from these 2 facts, but I think it requires a better explanation why that's the case. Somehow from these facts, it follows that twice the number of edges is greater than 3 times the number of regions. And it is true. But I want to explain it a little better. Or is it clear for people why that should be the case? If you're honest with itself, it requires better explanation, right? It's kind of makes sense what I just said, and it does make sense. It is true. All of what I said is true. Anyway, but let me explain it this way. Consider the same graph, and this is a general argument. Let me introduce a notion of a, what should we call it? Edge face matrix, okay? Or edge region matrix. Just as we remember, we defined those incidence matrices and so on. It's a very, very similar notion. So here's what I'm doing. Like, look at this. This is neat. So you have the rows correspond to edges, and columns correspond to the regions. So for example, for this graph, that matrix is going to be 7 by 3. Why? Because I have 7 edges and 3 regions. Okay, so fine. So I have that big of a matrix, no problem. Now, in this matrix, I'm going to place a 1 at the intersection of edge E and region R, I'm going to place a 1 if that edge borders that region. Otherwise, I'm going to place a 0. Example. Why is there a 1, let's say here, at the intersection of edge E3 and region R2? So here's E3 and region R2. Why is there a 1 here? Because edge E3 is at the border of region R2. It borders R2. Okay. Why is there a 1 here? Because that E3 also borders R3. Also borders R3. There's the R3 region. So in each row, for each edge, how many 1s can I possibly have? So let's denote by X. Let X the number of 1s in this matrix, number of 1s in this matrix. Okay, is it clear what X is? X is like the total number of 1s here. And what I want to do is I want to count the number of 1s first by looking at the number of 1s row by row, and then looking at the number of 1s column by column. So let's start with row by row. In each row, what's the max number of 1s that I can have, and why?
You can only have up to 2 1s.
Yes.
Because an edge can't border like 3 regions.
Yes, exactly. Each row I can have up to 2 1s. Okay, for exactly the reason you give, there's no way that edge is on the border of 3 regions. It is possible that an edge is on the border of 1 region, as we have with E7 here. Here, E7 just borders just R3 only, this guy. It's inside, completely inside your backyard. Okay, so you have this fence surrounding your backyard, and then there is just like from one corner into your backyard, there's this edge just jutting in. No one outside of your yard sees this edge. This edge is only inside this region that is in your backyard. That's it. So yes, you can have just 1 1 here, but there's no way you can have 3 1s in any row. Agreed? Okay, so X is less than or equal than 2 times the number of rows. Agreed? 2 times the number of rows is the number of edges. Number of rows is the number of edges, the way I've constructed this matrix. So that X, the total number of 1s, is smaller. Okay, at best is smaller. It's smaller or equal than twice the number of rows, or twice the number of edges. Also, by column. What's happening by column? How many 1s can I have in each column? It's like I can have a bunch of 1s. But here's my question. Can I have fewer than 3 1s?
No,
Why?
because each region has to be enclosed by at least 3 edges.
Exactly. No way I can have fewer than 3 1s. Okay. So therefore, do you see that the number of 1s in each column is 3 or more? And how many columns did I have? Do I have? How many columns do I have?
3 columns.
In this case, 3 columns, but what do they represent? The number of regions, right?
Yeah.
The number of regions. So 3 times, so X is greater than 3 times R. It's also smaller than 2 times E. So what do we have? So X is smaller than 2 times E, and it's greater than 3 times R. So conclusion. Must be the case. People agree? Must be the case. There's no other way. Proof. Need proof. A nice proof of why that's the case. Okay, so that clarifies that this must hold. Now I want to see that for any planar graph, I want to prove this guy. Well, why did I prove? I want to see why this is true. So why is that true? Well, then by Euler, who says that, what is it? B minus E plus R is 2. That is the case. Now, just to simplify life for us, how should we do this? Can we multiply this by 3 so that we don't have to deal with fractions? I'm just simply multiplying both sides by 3, please, right? Otherwise, I'd have to deal with the fractions like the book does something needlessly. 3e plus 3r, that is 6, right? Do people see that? Right? And because 3r is less than or equal, can I say that 3r, I'm going to substitute this with something bigger, like 2e. So can I say that 3v minus 3e plus something bigger, like 2e, and because I've for that term, I got something bigger, this is going to be bigger than 6. Do people agree? I've just substituted this term by something bigger, which we know to be bigger. And what does that say? Let's use blue here. So 3v minus e is greater than 6. So just rearranging the terms, what do we want to prove? That e, so let's use a different color. So e is at most 3v minus 6, which is what we wanted to prove. Every time you're able to place QED on your sheet of paper, that's kind of a satisfying feeling. Something depends on what you QED'd. It could be something major, it could be something minor. But either way, it's good to be able to place. You've completed the proof. Is this proof clear to people? So the number of edges in a by the way, it doesn't have to be connected, but in a connected planar graph, we know for sure that the number of edges is at most 3 times the number of vertices minus 6. Okay. Okay, so here's the proof, the summarized, what I've just talked about is summarized here. So, okay, so what do we have time for? Real quick. Okay, so we'll just read. Okay, so can we prove, what should we prove? Is K5 planar? Is K5 planar? Let's prove this one. Okay. If a graph is planar, then the number of edges must be this. How many edges in K5? Didn't we just prove it? So people agree that I've just proved this, right? People agree with that. So how many edges do I have?
It's 10 edges.
So is it 5 shoes? Why is it 20?
Oh, never mind. It is 10. That's
Yeah. And how many vertices do I have?
5.
Okay. Carry the 6, right? So what do I get? 10. So is less than or equal 9. Okay, so okay, let me just repeat what we have. The question I asked, is K5 planar? And I wanted to say, no, it's not planar, and I want to prove it. Here's the argument. Suppose K5 is planar. K5 is a connected planar graph, and for any connected planar graph, including K5, we just proved that this relationship must hold. So this relationship must hold for K5. We check this relationship. It turns out that it does not hold. Okay, therefore, K5 is not planar. Why? Because if it were planar, then this relationship would hold, and it doesn't. Make sense? That K5 is not planar. Final thing we should remark is that the converse of this theorem is not true. So can I claim that K33 is not planar? So this is the last thing. How about, do I have it? Yeah, how about K33? we're not going to prove it. This will be like either we'll discuss it next time or you should attempt it. But I just want to make a remark. Suppose I'm trying to make the same argument and I will fail in a minute. So this is like I'm failing here. Suppose yes is planar. Okay, so what's the number of vertices? Okay, so
six vertices.
Yeah, 6 vertices. So here's the relationship was this 3v minus 6 that we proved. No this. So the number of edges is, so v is 6, as you just told. How many edges?
9.
I have 3 times 3 edges, 9. So is 9 less than or equal 3 times 6 minus 6?
Yes.
Yes, it's perfectly fine. Can I conclude that this graph is planar or not planar? So this we must, like, this is like something we must grok and then we're done. What is the theorem that I just proved to you and everybody agreed? We proved the following, so please follow. So this is like the logic thing now. It's not math anymore. So P implies Q is what we proved. G is planar. We proved if G is planar, then something holds. That something was this relationship. Then E less than or equal V minus 6 holds. Okay, this is what we proved. We did not prove that if G is not planar, then this does not hold, right? It is the contrapositive, which is equivalent to it. It's true. If Q does not hold, that is true equivalent. That not Q implies not P. That is true. I'm not arguing with that. I'm just saying if not P, then not Q. We didn't prove. So here's what we have. K33, is it planar? Well, for this graph, Q holds. Q is true for K33. Can I conclude that P is true? That is, P stands for graph is planar. Can I conclude that Q implies P? That's the converse of the statement. So P implies Q is the statement that we proved. Q implies P is the converse. Did I ever prove the converse?
No.
I never proved the converse. I never claimed it to be true. Okay. In fact, it's false. This can be demonstrated very easily, but we don't have time for that. The point is that I never proved that Q implies P. So just the very fact that I proved that for this K33, this Q holds, proposition Q holds, that is, the number of edges is less than or equal than 3 times vertices minus 6. The fact that it holds does not imply G is planar, right? In fact, it turns out that G is not planar. Does that make sense? So the last piece was just logic, right? Just logic, right? But what we've proved, like the math pieces, those were neat little jewels, in fact. The fact that this relationship holds between the number for planar graphs and for Platonic solids, and by the way, not only Platonic solids, but for other structures, the 3D structures called Archimedean solids also, but we're not discussing them. Any questions?